Great. Okay, so I'm going to talk for about 45 or 50 minutes, and then I'll take questions until you drag me off the stage.
Okay.
Thanks a lot for inviting me tonight, as I said. Let me share my screen. We'll get things started. There we go. Nice logo. When I pulled it from your site, it was so tiny on your site. I went, oh, nobody's going to be able to recognize it. But it's a pretty high resolution image you've got on your site, so thanks for that. So how have we managed to discover so much about the universe when, we haven't really even left home, have we? Images, of course, we've been capturing for, 150 years or so. But we even can get a sense for depth, a third dimension, during a total eclipse. And now, by the way, just a quick question. Can you see this little stamp I'm dragging around on my screen of video previews or not? You can't. Good. Okay. No. Just wanted to make sure what you could see. And if we wait a while, we can see the time dimension. You can see some stars. There's one in the upper right-hand corner, for example, that are going on and off. These are standard candles. This is a time dimension. But if we spread the colors out, we get an as if, notice the air quotes, fifth dimension. I love this. Just even aesthetically, it's gorgeous. The colors are beautiful. It's fun to just try and figure out, well, where does this blue become green? Where's the transition occur? But those gaps are part of what we call the spectra, and they reveal things about our sun as well as other stars, their composition. And there's examples on the right I'm going through here. I'll show you some of these during my talk. I won't go to the trouble and torture you by reading my bullets. But spectroscopy, about 80% of the research that gets done in astronomy uses spectroscopy. So even if you're not even thinking you want to do spectroscopy, maybe you're an armchair astronomer or use binoculars. So this really isn't something you'll ever do. By understanding a little bit about it and how it gets done, I think what you'll find is it deepens your appreciation of some of the things that we read. I know when I read things in the magazines, I tend to be sort of a little passive, which is, I think, a euphemism for lazy. I'll read something and sort of, I sort of understand that, especially with our short attention spans these days. So being an active reader means that we bring to our reading a little bit more understanding, and spectroscopy has helped me do that. So a little bit of science just to get everybody up to the same level here. Sir Isaac Newton discovered that you could put light through a prism and split it into its component colors. You can also do the same thing by bouncing light off a finely lined surface, or even passing it through a piece of glass that's finely lined, called a diffraction grating. Bunsen was pretty cool. He invented the Bunsen burner to burn a sample, to put the light through a prism, and look at the result. He was a pyromaniac. He burned everything he could find. And the good thing is he kept great records. He created a catalog of the things that he looked at and what their spectra looked like. And we'll see more about that in the next few minutes. One cool thing about him is he deliberately, and he said this straight out, he said, I'm not going to patent the Bunsen burner. I want it available to help humanity and to help anybody who wants to further the benefits of mankind, womankind too. So today, of course, there'd be a handful of patents on the Bunsen burner. This guy on the right, Kirchhoff, he was a colleague, co-worker, contemporary, and we're not going to get into a lot of detail with him, and only one thing on this slide here, and that is, notice this spectrum here, it has like a rainbow in the background, right? The Roy-G-Biv rainbow, and it has some gaps called absorption lines. And compare that to this spectrum here, which has more or less a black background. Dennis, did I scare you away that fast? Black background with some emission lines. Now, which you get depends on things we're not going to talk about, but Kirchhoff did. The temperature and pressure of the gases that the light's going through. None of that matters for us tonight. But one thing to look at is that the lines are, especially if I use the right key, the lines are in the same position whether they're absorption or emission lines. And we'll see examples of both of those as we go through my presentation tonight. So these lines are chemical fingerprints. And for example, you can see this hydrogen line just doesn't exist in helium. And in fact, hydrogen is so common in the universe, and we use it so often in spectra, that it's nice to know the name hydrogen bomber lines that refers collectively to the lines that we've even given Greek letters to, much like we give Greek letters to the stars in the constellations by intensity. This is just by position. So there's our hydrogen alpha in the red, and That's what robin egg blue and the beta, hydrogen beta there and so forth. So, but notice, as I said, helium, like the helium you put in a balloon that you blow up or have blown up at a florist, it doesn't have a hydrogen alpha line. Let me tell Outlook, or excuse me, PowerPoint here to keep my arrow always visible. There we go. This is a periodic table I created a few years ago, and we sell them mostly to schools and to the real, the nerdy, and I mean that in the nicest of ways, nerdy amateurs. The cool thing is, again, you get to see really clearly. There's that hydrogen alpha in the red and this robin egg blue beta, but notice how different helium is. And this is a great poster that, like I said, educators hang up in their classrooms and hallways and things. Neil deGrasse Tyson told me he has one hanging in his office, so I'm particularly delighted about that. It's a little bit longer a story than I have to tell in my primary presentation tonight about how he got it and how I had the opportunity to meet him. This is just an example of my software. You can see in the background here, that's a gas tube. We don't have to burn things anymore like Bunsen. In fact, I've got a gas tube over here. You can see I turn it on. It glows, yippee-doo. This is one of the gas tubes. This is a helium gas tube here. And that's how we study gas tubes in the lab and in classrooms today. I actually took my software and adapted it to a camera that we created a few years ago for educators. And we have a lot of these in high schools and colleges, astronomy, physics, and chemistry teachers. So that's been a lot of fun for me. So far, pretty much everybody I've mentioned have been old white men. Let's look at some of the non-old white men. Annie Jump Cannon and her group of women called the computers were prohibited from accessing the telescopes at Harvard a little more than a century ago. So what they got stuck doing was looking at the glass photographic plates of spectra. And they were fantastically good at it. And they cataloged hundreds of thousands of stars. And with that much data, they also were able to observe patterns and come up with a very ingenious category system to understand the classifications of stars, and it basically invalidated all the previous ones that had been created that just didn't quite fit. Priyamvada Nataraja is at Dartmouth, and she studies hyperactive black holes. You may recognize the name Nancy Grace Roman. There's a telescope that's coming up with her name on it. She was the first astronomer at NASA. She got her PhD in the late 1940s. This is a Hubble Space Telescope. She was a big proponent of it and really pushed to make it happen, thank goodness. Elisa Quintana studies exoplanets around red giants, interesting in itself. And finally, Jedediah Eisler's at Dartmouth, and she studies gravitational lensing around black holes. Again, we haven't come that far. We've come somewhat in elevating and giving opportunities to non-old white men. I thought this would be a good slide to show just to remind us we still have a ways to go. This was a fun slide to put together this summer. There are so many women in the field that we haven't heard of, and this is just a small number of them. So what I'm going to talk about tonight is this star analyzer grading. It's an 1.25 inch grating. I'm just unscrewing it from its mount here, just like this. And it splits the starlight because it's got many lines adjacent to one another. It's only $200. In fact, I forgot to bring it down. I have like a little, one of those chimes with a hammer that they'd use at the end of like maybe a meditation session or something, or give it to a 3-year-old to drive you crazy. And I was thinking I would chime every time I brought up a point that was, part of my message. I used to have a list of 10 bullets that I showed at the beginning, but that got too boring for all of us, including me. So this is one of those chime points. The myth is, gee, spectroscopy is going to be expensive. The truth is, for a couple $100, you can do some really cool stuff. So here's different ways that you can mount the grating. On the upper left there, you can see it's on the nose piece of a camera, and there's a little adapter that threads into the lens cap threads. And that's sort of a cool way to do things, but it's not a lot of aperture. You can do it, especially if you've got tracking. Over on the right, again, just an example of a FITS camera. It can be cooled, non-cooled, doesn't matter. Almost any camera, like I said. This is a ZWO color camera. It can be color, it can be mono, or you can even put it in a filter wheel. So there's lots of ways to mount these things. So this is a chime moment, and that is, geez, it's going to be really hard to configure my setup to be able to do spectroscopy. That's the myth. And the truth is, most of the time, you just screw it on right onto the lens cap, or excuse me, onto the adapter threads. Okay, so This is just an example of the kind of thing you could do with a DSLR, piggyback it, and then you could do some other kind of imaging at the prime focus. All right, so that's the history, theory, a little bit about the equipment. What can we actually do? That's where the fun is, right? So we take a star, we put it we take it. How do we take it? We grab it. We take a grating, we put starlight through it, and it splits the light like a prism into a spectrum that we can image, and here you can see it on our sensor. Check this example out. This is just gorgeous. So these are different spectra captured at different times by Torsten Hansen. You can see at the top there, just with an 8-inch Newtonian and an imaging source video camera, much like the ZWO cameras that are more popular today. The stars or the spectra here are in temperature order, starting with the B stars and then going down through the A's, K's, and M's to the cooler stars. Those are in Obia fine G KM order. I don't really like that acronym because it just feels a little bit dated. So there's another acronym which I forgot to bring up on my phone that I took a screen capture of the other day. It begins OK Boomer, but I can't remember anyway, I'll find it while we're in the Q&A. It used to be easily accessible on my phone. My apologies for not being able to find it. So, but you know, I said one of those original bullets I listed about things you can do includes star temperatures. Just look at that. As the temperature cools off, look how the spectrum changes. So we'll look at two quick examples here. First example is that it's not a line. That's actually like a forest of lines. It's called a band. And notice those are really on the cool stars. We don't see those on the hot stars. Well, what that is the outer shell of the star is cool enough that some more complex molecules can exist without getting incinerated. Now, again, these are type M stars down here. So that's why we can see these on the cool stars. I don't know anything more about these bands other than their titanium oxide. And this is like a ding moment. I may like doing it that way instead of with the actual ding. The ding is myth. I need to be an astrophysicist in order to do spectroscopy. And the truth is, listen, if a knuckle-dragging programmer like me can do it, I don't have a PhD or an undergraduate degree in science. You know, we're all interested in science. And the cool thing about doing it when we're not in school is we can learn as much or as little as we want. So I didn't care to learn anything more about titanium oxide, nor need you, unless that's something that interests you, and then you can dive in. The other feature I wanted to show you here is that line there down around 4800. That's in the Robin blue, right? So that's our hydrogen beta line. Notice that it's much more prominent there. It's darker than there or there. This is on a type A star. Why would that be? Well, again, it's temperature dependent. It seems pretty evident there. Centered on the type A star like Vega, for example. Let's talk just a moment about how these lines get created. Remember, the Bohr model of the atom has these shells, and there are electrons in the shell. Now, when an electron gets pulled up by heat or energy to a different shell, that absorbs energy. That's how you get that line. And so with these hotter stars, they're so hot that the electrons don't stop at 4, they keep going. That's why there's fewer or a dimmer line here, because there's fewer electrons. Same thing with these cooler stars here. The electrons just don't get pumped up to level 4, many of them. So the 4 to 2 or the 2 to 4 transition is what gives us this hydrogen beta line. I should have said that first, in the Robin egg blue. So it's temperature dependent, and we can tell something about a star's temperature by looking at what lines are visible. And that's how professionals do it. So now you see that crosshairs there. Now, there actually is a slight dimming in that Robin egg blue region. But, you know, if I was to get time on the Hubble Space Telescope with their spectrometer and I captured some star and I wrote a paper and said, yeah, we saw a little dimming in the Robin egg blue, that doesn't get published, right? It's too qualitative. To do science, we need to be quantitative. So what we do is we create a graph of this region, of the whole spectrum. So the star is bright and narrow. So this peak, given that this is the intensity scale here, this peak is high and it's not very wide. Whereas this thing is really wide and is dim, and then it gets brighter, 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 and then dimmer, dimmer, dimmer. So this goes dim, brighter, 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 dimmer, dimmer, dimmer. But here's the cool thing. look how that barely visible dip in the actual image is really clear here. Now we're doing science. Now we can look at the width of it, the location of it, how it compares to this star the next night or to other stars or to other instruments. Pretty cool. So how do we get that graph? So my story is in 2009, I just wanted to do this stuff. I don't know how I came up with it. Somebody in Q&A asked me that the other day after a talk of mine. I can't remember, but I wanted to do it. I got a hold of a grating of some sort. I put it on my C8. I'm 3 miles from downtown Seattle from Pike Place Market. I went outside, right outside the window there in my backyard on a Saturday night. I looked at Vega. I had it. I actually have it here somewhere. I don't know where it is right now. Talk about not being prepared. This is something I don't need to show you, but I actually used a webcam, and it still got all the adhesive from the duct tape as I duct taped it to my telescope. I came in at midnight. I had some video. In fact, this is a frame from that video. And I was not a great imager. In fact, ding, what you're going to find is that the examples I show you, you won't find this unless I tell you, but I'm going to tell you. And that is, this stuff is easy. I was not a great imager. I really wasn't. I wasn't into it. I just didn't enjoy the subtleties. And I'd look at those books that had a before and after picture of some image process, you know, and I'd go, I guess I see the difference between the two, but it just didn't excite me. So even somebody who's not a great imager can do this kind of thing. Now, the example I showed you a few minutes ago was like with a video camera. It's not like, you know, those images in the back of the magazines that are just gorgeous. They're beautiful. Then you look at the fine print. Now, Astronomy magazine doesn't publish them. I noticed the Sky and Telescope does. And, you know, at the bottom of the caption for the images, it'll say, you know, Joe Schmo or Jane Schmo captured this. It was 45 hours of integration time. I'm in Seattle. I don't get that much dark sky without clouds in a month in the summer. So I don't have the skills, location, equipment, or patience to do that kind of imaging. And nor do you need to have that to do this kind of thing. So when I came in at midnight, my neck was sore. I had grass stains on my blue jeans because it was Vega in the middle of August, right? What do you expect? And the next morning, Sunday morning, I went to create this graph with some of the freeware that was out there, and I couldn't get one of them to even install. And it was like DLL hell. And none of the software I found would do it. And the problem was it was crashing. Literally half of one of the programs was in French. So it would pop up with these unintelligible error messages. And it just wasn't up to the usability standards that we've become accustomed to. So what did I do? I gave up. I told my wife, I said, look, this is a hobby. I'm supposed to be having fun. I'm just frustrated. And who likes learning new software, especially when it sucks, to use a technical term. So I gave up. I put the grating in the drawer, but it weighed on me. I really wanted to do this. So a couple weeks later, I decided one lunch at work that Saturday, I'm going to write a program to convert this to the graph like this. And I did it. Sunday morning, I had the graph. And now, 10 or 15,000 hours later, the software is almost done. This isn't true, but it's a fun line. My wife keeps saying, would you finish the software so we can have dinner at a reasonable time? It's done. There's always improvements. They say any software that's bug-free is archaic and out of date. And that's not the case here. It is bug-free to my knowledge, though. So how do we create this graph? I think one of the obstacles, and this is a ding moment, one of the obstacles is to learning something new is, oh no, I'm going to have to learn a new piece of software. Now, I can't give you a software demo right now because it's after dinner and I know we'll lose more than half of you if I spend more than like 2 or 3 minutes showing the software. But I want to show you how easy it is to do this stuff so you don't come away going, well, yeah, it's another real pain in the neck for software. You know, I'm just going to have to learn some new, unique something or other. So let's look here at the software. So this is an image from a FITS camera, like I said, bitmap, JPEG, FITS, color, mono. It could be a freeze frame from a video. There's a star. I like color when I'm showing people the software and doing education or sidewalk astronomy because it's much more intuitive what's going on here. Notice there's a gap there. There may be some gaps there that you can see. So all we do is bracket in the region that we want to study, and we see that intensity graph. So this peak is the star, right? And this thing over here, which means that that dip is that dip there. Well, that's all well and good, but who cares? There's a bunch of tips, right? So remember I mentioned that Bunsen created a huge catalog. So the great catalog from Bunsen, now almost, 180 years later or so, a little less, that catalog we still use today, and it's embedded in the software. So I can come down here and say, show me on the graph where the Balmer series would be, where there would be dips if this star had hydrogen that was subtracting light as the light left the star because of those electron transitions. And wow, we've got matches there, there, there. That's fairly conclusive proof that we have detected hydrogen on this star. Pretty amazing with a backyard telescope. So this fill here is eye candy, but it makes for really good outreach, especially, this is actually a freeze frame from a video that plays at 2 frames per second. Let me play that video. So it's playing now. Notice there's the star, there's the spectrum moving around. Notice that our data is jumping around from seeing, right? This is a fantastic outreach tool. It's a way to take people, public outreach, or even at a star party, take people to the next step. You don't need to be an astrophysicist to explain to people what's going on here. You just read the Wikipedia pages a few times and confess when people ask you a question you don't know. In fact, in Q&A, you may ask me questions that I don't know. I'm like a really broad river that's really shallow. So, but I love how interesting this is visually. Now, the other really interesting thing, and then we'll leave this screen, notice that absorption feature right there, that's our hydrogen alpha, that's our hydrogen beta. Notice that feature is sort of coming and going and moving around a little bit. Sometimes you can see it, sometimes you can't. We're all somewhat familiar with this concept of stacking images to remove noise. Let's turn on stacking. Watch how quickly at 2 frames per second, that image, that absorption feature becomes fairly symmetrical and stable. At 2 frames per second, that took what, 5-10 frames. So that's really what I wanted to show you in the software. I'm going to turn on the eye candy again. So there's that hydrogen beta in the robin egg blue. And as we leave this screen, I just want to ask you, if you would, just in your mind's eye, remember that view. So this happens to be Vega with absorption lines, but mainly these are the Balmer series lines where hydrogen would be absorbing if the star had hydrogen, because I'm going to show you some really cool scientific discoveries that were made with that kind of data. So here's a star party I mentioned earlier, how interesting this can be to people because it's color. You might not do this at a dark sky site with all that light. They're looking at a gas tube here, and then they transitioned over to a star. This is actually shot in France. Here's a wide field view to give you some of the color. Unfortunately, visually through an eyepiece with a star analyzer, you don't see this that clearly. It really does require a photographic image. So here's a few stars and their spectra. There's an absorption feature. Here's another star with some lumps, right? Those are emission features that have saturated a pixel. And again, we just have some blooming going on. Let's look at a Wolf-Rayet star here. So I have a confession to make to the group. When Janet Simpson sent me this spectrum about 8 or 9 years ago, I couldn't remember what a Wolf-Rayet star was. I knew it was a type of star. It wasn't some made-up word like Gagaboo star, right? And I recognized it, and I'd probably read about Wolf-Rayet stars a handful, half dozen times over the years. But things do go in one ear and out the other, especially as we get older. So Wikipedia is our friend. Real briefly, Wolf-Rayet stars are, that's my English accent, Wolf-Rayet stars are, I think there's no L on the East Coast, so you say Wolf-Rayet. Their late-stage stars are 25 times as massive as the sun, enormously bright, intense stellar winds, end at their life, nearing the end of their life cycle, maybe going to become a supernova. And because the outer shell is dissipating, we can see a little bit into the star and see some of the more composition. And what we see on this emission spectra is carbon, carbon, carbon. Why would there be carbon in a star's emission? Well, remember, stars burn through the different elements, hydrogen, helium, and so forth. There's things called the CNO cycle, all sorts of things. And that's, the carbon is an intermediate product of that burning process. And we're seeing it with 30-second exposure with a DSLR. Pretty amazing. Let's look at, these are emission lines. Let's look at another popular, well-known emission object. Here's the Ring Nebula. Now, it only has two different colors because there's really only two main elements that are burning. This red hydrogen alpha and this oxygen. That Roman numeral 3 just means ionized. It means electrons have been pulled off. So this is pretty much the only extended object that looks interesting without a slit. A slit makes things visible, spectra visible on objects that are extended. For example, let's just look at just real briefly. Here's some examples of slit devices. You can see they're like an order of magnitude more expensive and perhaps equally that much harder to use, because now you have like a 10 or 20 micron slit that you're trying to acquire your targeting guide on. There's a lot more to them. So almost nobody, like 1 in 100 starts with those. Just the learning curve as well as the expense is too high. So here's an M42 done with a slit spectrometer. It's an extended object, but notice how nice and narrow this hydrogen alpha, and there's that ionized oxygen with that Roman numeral 3 again. So in fact, because you're a fun group and like socializing, I'm going to stop sharing my screen for a second and ask for somebody to step up to the plate if you want to. I won't call on anybody, to tell us the first time you saw M42. It's fun to hear. Where were you? What was the telescope? What was your impression? Does anybody want to share that experience? And if you don't, that's okay. You'll have to unmute yourselves to do it. Anybody? Bueller? Anyone? Anyone? I got Joshua to smile anyway, and Rob. Okay. Also, you good, and more. Robin too. I want to ask you about that double B in your name before we're done tonight, Robin. By the way. So let's share this again. So my experience, since you were not forthcoming, was it was in the early 90s. I didn't own a telescope. I never had. I wanted to see Shoemaker-Levy 9. I went to the Denver Astronomical Society first quarter open house star party downtown. I walked up to got out of my car, walked up to the viewing field, and you know, it's sort of interesting when you can remember when you didn't know something. Well, I looked out at that viewing field, and what I saw, to my uneducated eye, you know those cannons that they used to shoot people out of in the circus? That's what I'm going, what? This doesn't make sense. This cognitive dissonance. This is like supposed to be telescopes. Of course, they were Dobbs, but I'd never seen a Dobb before. Anyway, I queued up. Somebody like some of you or me were running a Dobb. They were looking at M42. I'd seen pictures of M42 in the magazines. I was all excited. I got up and looked through the eyepiece. It was, you can predict, it was disappointing. And that was the story I was looking for from one of you. It makes a more compelling story if it's from one of you. So, some of you probably went through the same experience I did. And yet, you, like I, still go back and look at M42. Why would we do that if it's just this mono smudge of nothing? Well, of course, our telescopes are better now. We're observing at dark sky sites. And also, we've got much better at averted vision, right? So now we're really able to see things with the more sensitive parts of our eyes. And that helps. But really, I think even without all that, one of the reasons we go back and look at M42 is because now we understand more about what we're looking at. We know it's a stellar nursery, birthplace of stars. The point is, this is a ding moment. When we use the telescope, the more, what a silly way to start a sentence. When we observe things, the more understanding we have of what we're looking at, the richer our experience is. And you know that from your observing over the years. And I found that, this is a ding moment too, that spectroscopy and the little bit of reading that it impelled me to do has really helped with my visual observing and my reading. So, enough yammering, let's look at more examples. So here is the spectrum of the spectra of Uranus and Neptune. And there is an absorption feature and a band. Now, what does a band mean? Of course, I mentioned earlier, a band means a cooler object where some complex molecules don't get incinerated. Well, Uranus and Neptune are cooler than a star. And what would be that complex molecule? How about methane? So we're now in the backyard, same guy with a video camera and an 8-inch telescope are observing the methane atmosphere of these planets. So in 1881, Henry Draper, new topic by the way, observed the spectrum of a comet. Heck, if Hank can do it, why can't we? And we can. So here on the left bottom is the spectrum of a comet. There's the profile graph with these nice, beautiful peaks called the swan bands, mostly carbon, for a different reason than we saw with the Wolf-Rayet star. This was captured by a guy in 2013, Vikrant Agnihotri. He lives in Northwest India. He's a nuclear power plant engineer. And at that time, he was a newcomer. Now he's an expert, and I'm learning from him instead of vice versa. And what teacher doesn't like to see their students surpass them? So it's wonderful to see the work that he's doing now. But here's a more contemporary example, NEO-WISE. We can see the sodium in the tail here. And this was done with what's called an objective grating. I don't have my DSLR out right now. It's on the shelf behind me. But this is just when you screw the grating right onto the nose piece or the lens cap threads of the DSLR. So there are times when an objective grating on bright objects like this, and even some stars, can give really superior results. And that's something that people talk about somewhat in our online forum, where they're just experimenting with different configurations. Now, I really like this slide. Anybody who uses a C-clamp as part of their setup, that's my kind of amateur. Even though I break everything. In fact, you know, in real life, my favorite keystrokes in Windows are Control-Z or Edit Undo. Because, I mean, he used this to attach the camera to, again, his tracking mount. It's a video camera. Now, my problem is if I did that, I would crank down that U-clamp so tight that, that I you know, crush the camera body. He didn't do that. This was done by Robin Leadbeater, who's the designer of the Star Analyzer. He put a grating on the nose piece, and he aimed it at the Perseids in the sky, or where the Perseids would be. And right here is a single frame that he captured. So in the period or the time of one frame, which was like a half second or a quarter second, the meteor moved that distance. And the spectrum is over here. And for example, that gap there is that dip in intensity there over on the right. So this is sort of a rather esoteric branch of amateur spectroscopy, but you know, there's all sorts of things, whatever floats your boat. So I won't talk much about the sun tonight. We've heard a lot about it in the last few years and will again in the next several years, except to point out that in 1868, these two old white men observed this yellow feature in the sun during a total eclipse. They didn't have slits, so they needed a really narrow object like during a total eclipse. And they went to Bunsen's records from like the previous decade, and there was nothing that he burned that had a yellow line like that. And they went, what, WTF? They went, we don't know what that is. Let's give it a name. The Greek name for sun is Helios. We'll call it helium. We don't know anything about it except it glows yellow when we burn it. Now you fast forward 3, 4, 5 decades. In the beginning of the 20th century, a couple observers were burning some gas that they had created through some experiments, and it glowed with that same color. And they were able to say, eureka, that helium that we observed on the sun and knew a physical property of, we've now observed here on the Earth. I love that story because it's such a great example of how science can be done, where we knew something, a physical property, and named something that was 93 million miles away before we even had it in hand here on Earth. I don't know whether having it in hand refers properly to a gas, but you get the idea. So if you're into novae, some novae, as you can see here, have absorption features for iron, some don't. You can even do that with the DSLR. Quick review of Doppler shift. Most of you will recall that if a car or a sound goes past you, as it's coming towards you, its horn is higher pitched, and when it's moving away, it's lower pitched. So, right? Or train whistle through a station. High as it's coming towards you, low as it's going away, because the waves are as if stretched or compressed. Well, the same thing for light waves. If we were expecting to find this triplet in the spectrum, and instead of seeing it right there, we found it shoved over to the right, we'd know that object was moving away from us, and that was redshift. Or if it was shifted to the left, we'd know that an object was moving towards us, or blue shift. Let's look at what we can do, because Doppler shift is a huge piece of astronomical research. So there's, as you know, lots of different types of supernovae. One type is called a type 1a, and it's when a bigger star, some of its gas ends up on a white dwarf, and when you pour gas on something hot, it explodes. Let's look at an example of a type 1a supernova in M101. There it is. There's a photograph of a different type 1a supernova that's in our galaxy, same type. You can see it looks like it has this spherical shell around it, doesn't it? So here's the spectrum that David Strange captured with less than 15 minutes of integration time with just a 9-inch celestron and a star analyzer. And there's the spectrum. You can see a little tiny absorption there in the image, but very clear there in the graph? Well, you know, we talk about, it's almost overused, the standing on the shoulder of giants. But the giants figured out that there are different types of supernovae, right? There's some where they just run out of fuel, one star, and it collapses, core collapse, as opposed to this binary. The previous slide I meant to show you, I just noticed this the other night. It says binary pair. Well, how many stars is that? Is that like 4 stars or is that 2 stars? Binary system probably describes this a little better. Sorry for the diversion. I was just laughing at that the other day. So this binary system, the giants have figured out, always have a really deep dip right here around 6,000. And that's ionized silicon. That dip means it's a type 1a if it appears down at about 6,000. Notice these other supernovae here don't have a deep dip there. They have other identifying features. Like if you saw this big peak here a little higher, you'd know you had a type 2 supernova, which quite frankly, I have to confess, I don't know what that is, but I will tomorrow. It's the first time I've admitted that. So we as amateurs, if we observe a deep dip around that wavelength, we know that we're observing a type 1a supernova. And that's one of the things the professionals would like us to do for pro-am collaboration, is there is a catalog of supernovae that have been discovered where they haven't classified it as to whether it's whether it's a supernova or just some other sort of eruptive phenomena. So we can do that for them. The bad part about that is most supernovae, unfortunately, are in other galaxies. We don't see them that often here, and they're pretty dim, so you need a fairly big telescope to do it, but it's doable. But here's the cool thing the giants did that we can do too. David Strange and I both observed that the wavelength here was at around 6150 for that deep dip. So we made note of that. Now stick with me here, it's pretty simple. Now here on Earth, if Bunsen had burnt beach sand, silicon, he would have observed the emission line or absorption line at 6355, which is really different. Well, that difference is because of Doppler shift. Something's moving. I wouldn't have known the Doppler shift formula if it had bitten me on the butt. I hadn't seen it in half a century, maybe. But Wikipedia is your friend. When you plug the numbers in, we have now calculated the speed with which the blue shift from that expanding shell is racing towards us. Pretty amazing. With a backyard telescope, isn't it? So you may recognize this guy. He and his team just before the turn of the century observed the accelerating cosmological expansion and won the Nobel Prize for it. And what do you think they used for their standard candles? Type 1a supernova. I don't think they used our grating. We get a lot more bang for our buck if that's a ratio than he does with his $1 million. I mean, it's debatable. I don't know how you measure bang. But again, it's fun that we can do this kind of thing. So what about the spectrum of a black hole? What would that be like? Well, black holes, of course, don't emit light, but the accretion disk around it as the matter spirals in gets very hot and creates an emission spectrum. So David Strange, who's south of here in Portland, I've never looked at 3C273. He did, and he captured its spectrum. Now, again, this is not something that some wizard on a mountaintop with a 24-inch telescope captured in 20 hours. This is David Hayworth, as well as countless other amateurs have done this. This is, again, I think it's important that we talk straight here, and that it's not that I'm showing you things that might be possible in a decade if you work really hard. So you see on those two right-hand arrows, there's 2 little points of light. Let's zoom in on that. And there are those points of light, and there is the spectrum. Notice those big peaks and some others too that we can't quite visually see here, but show up really clearly. Now this guy, Martin Schmidt, he was in his mid-20s in the early 1960s. He looked at this and he was trying to figure out what those peaks were. That's what science is, right? And he was really frustrated. And the reason I know this is there's a fascinating transcript of a long interview with him where he describes this whole process of discovery. It's linked to on my site. If you can't find it, you can contact me with the contact form and I'll send you the link. He got really frustrated. He couldn't figure out what those peaks were. So he decided, okay, I'm going to go back to square one. Like much science, what he decided to do was to eliminate things that those lines or those peaks couldn't be. So he grabbed a reference for hydrogen. So there are the hydrogen bomber lines I suggested you keep in your mind's eye from my software. It happens to be a spectrum of Vega, but the important thing here are those blue lines are where hydrogen is going to absorb or emit light. And they don't line up, do they? So when we look at this line here, there's no peak. These peaks don't line up at all. Of course, I showed you the punchline by going too far. They do line up. And he figured out that this object was massively redshifted from cosmological expansion. Using the Hubble constant, he could calculate the distance that this quasar was away from us. Amazing, 2.5 billion light years away. What's astonishing is that light that's that old and has come from that long a distance still has embedded in it enough information that we can tell something with very simple equipment about what that object was like back then. That light doesn't seem to age. Now, here on Earth, things age a little differently. Here's Martin Schmidt a few years ago. I've been justly accused of throwing rocks in a glass house. I mean, he's got a full head of hair, right? So it's just that I'm envious of him. Fact being, though, that my wife tells me I'm supposed to dress for success, and I think this is probably the perfect thing when you're doing spectroscopy. I know it's a mess, but if you look down in here, you can see there's the hydrogen alpha line right in there. But as far as the mess goes, you know, off the record here, and I know some of you have experienced this at home with your partners, perhaps, or yourselves. We're all about color in spectroscopy, right? If you look down in here, it's no longer red. It's starting to get into the gray. In my salon, they're not picking up the phone. You know, I can't make an appointment. It's just, like I said, some of you may have experienced this on your own. So let's look at one other example here. And then, well, I've actually got 3 more. Let's go quick. So, no, actually just 2 more examples. Good. So suppose we wanted to zoom in on that hydrogen alpha line. There's alpha, beta, gamma for Vega. So it would be great if we could just take our mouse and scroll our our little roller wheel here and just zoom in. But that would be like adding empty magnification when we're looking at the moon, right? At a certain point, there's just no more information there. You can zoom in, but it's just going to get blurrier. So same thing with spectrum. In order to zoom in on these features, you know, with a slitless grating, like the star analyzer, our resolution is about 50 angstroms. Let's look at what this looks like with a slit device. Wow, nice and sharp. This is that feature. So, and these are probably all different elements. So like a lot of science, what we'll do is we'll compare this to another object and see how they differ. Let's put the spectrum up of the moon with reflected sunlight. Now the moon isn't moving towards or away from us. So the moon is at a different spot. That difference is due to the Doppler shift from the radial velocity of Vega. So, and the numbers can be calculated, and we can calculate fairly close what the radial velocity is with just a backyard spectrometer. That's amazing. So this is my last example. I hope you don't feel like you've been drinking from a fire hose. I know I've gone through a lot of examples here. So this is a really fast rotating star, okay? So this edge is coming towards you, and this edge is moving away from you. So the light coming to you from here is, I can never remember, is blue shifted, and the light coming to you from here is red shifted because the star is moving away. And the light coming from here really isn't shifted red or blue because that part of the star isn't coming towards or away from you with reference to rotation. Let's look at what that looks like. So here's Vega. That'll be our standard. And here's a graphic representation of what I just showed you with the basketball. It's rotating this way. So this edge is coming towards you, you have blue shift. This edge is moving away from you, you have red shift. And that's what the spectrum looks like, that blue line. So what's happened is some of the light that's normally here has been shifted over to here, and some of the light that's normally here has been shifted over to here. So we have that broadening. The giants are really smart men and women. Who would have thunk that with just simple equipment, this is also done with a slit device, with simple equipment, you could detect the rotation speed of a star that's, you know, countless light years away. So really pretty amazing. Okay, let's finish up here. If I turn that off and go there. So you need a grating to get started. You need a camera, as I said, most any camera will do. You need software. My software, as you've had in your face down here for a while, R stands for real time because you can do real time video under the stars. If you, by the way, if you're doing static imaging, you know, you've got a FITS camera and you're running it with whatever software you're running it with, you continue to use that. And then my software can be configured to automatically pop open any image that shows up on your computer. So it's like pseudo real time. You snap an image. There's an archaic term, snap. You know, it's onomatopoetic, I think, you know, with a camera is snap. So most any camera, my software, this is the software I mentioned I had tried 10 years ago. I know these authors. In fact, I was in an AVSO workshop with them last weekend. Great people, great software, really steep learning curve. And still, they admit it. You know, they're not software professionals, so it just doesn't have the usability. And you may need a thread adapter. And the reason for that is, or a spacer. We want the grating to be approximately the right distance from the sensor. It's not like focus, it doesn't have to be exact, but you don't want it too far away or too close. So we have like spacers for $10, and there's a couple things. There's actually a calculator on my site where you plug in your specs for your telescope and camera. And if it gives you these green flags over here, you know you're good to go. Frequently people with my offer here will just click on here and fill in a form with their equipment. I'll send back a 2-minute video where I fill this in and I explain to them what they need in order to get going. I love doing that. I spend a lot of time, you know, just supporting newcomers. I love seeing people get up to speed. So books, lots of great books out there. My site has a link to books like this Spectral Atlas. This box should be around links. I keep forgetting to change that. This is that book I pointed out a moment ago. It's really a remarkable book because, you know, there's going to be a lot of dips in your spectra. How do you know what they are? Well, the cool thing about him is, and his book, is he has all these samples where he says, you know, if you're observing an object like this, and you can do this object, by the way, with just a webcam, if you see two peaks like this, one's oxygen and both are oxygen actually, but there's nitrogen. Well, for a knuckle dragging programmer like me, it's like, so what? What does nitrogen mean? What's the significance of that? So his book, in addition to those great diagrams, has a whole bunch of prose aimed at us, not astrophysicists. And he explains what we're seeing. So there's lots of books listed on my site that are interesting. There's forums galore. Our forum is quite active and very accommodating of new people. Last slide here, I think, maybe two more. My software is free for 30 days. I gave a workshop, as I said, to the AVSO last weekend, one in August, and 4 years ago I gave one at a conference down in LA, the SAS conference. And it was a hands-on workshop. So everybody had their laptops and some sample data I had provided for them before the workshop. And I walked through using my software for about an hour, and they followed along and asked questions. Well, the good news is that was recorded and it's on YouTube. And the sample data is available. So you could download my software tomorrow morning, and you could download the sample data from this link here, same place, and then you could follow along with that YouTube video. It's nice to have two screens if you're going to do that. So even if you were never going to do spectroscopy, if you work through that workshop for an hour or two, you'd really have spectra in your bones and you'd understand a lot more about it. Be in your muscle memory. There are pro-am opportunities. These are all amateurs up here in this professional paper. There are more opportunities coming regularly. The AVSO now has a spectra database. And much like their photometric database, it's beginning to accumulate data that will be valuable to professionals. The value that we have to professionals is changing because of all the spaceborne telescopes now collecting terabytes of data. But what they can't do, and we had one this weekend tell us, a professional say, what they can't do are the high cadence observations over a period of time, the longitudinal time studies. They can't get time on their telescopes to do that. They can't get time on their telescopes to look at more common objects that are believed to be understood. And they can't observe really bright objects. I don't know if this is true. I have to ask somebody. I claimed this in my last talk with the same disclaimer. And that is, I don't think the Hubble can look at Vega. I think it's too bright. So, but we can. So we've come a long way on the shoulders of giants in the last 200, 300 years. And we've come a long way in the last, geez, it's now 53 minutes. My apologies for going a little over. I love the topic. I really appreciate your inviting me here tonight. I saw some smiles at some of my silly jokes. Thank you. There's all sorts of ways to contact me. I'd love questions, whether they're here or sometime in the future. So let me stop sharing my screen, and you can ask questions until there aren't any, and then I'll go upstairs and finish watching that soap opera I was watching with my wife. What's up? Questions?
Yay!
Thank you.
Tom, thank you so much. Oh my gosh, so much information.
Yeah.
In such a short amount of time, my head is exploding.
I debate. I
gotta go to your website and just,
You can go to the website, because the samples page has a lot of these samples, and the recording that you're making will also be something you can review. It is a lot of information, and I try and cut down. It was actually longer once upon a time, and I just don't know what to remove. They're all such beautiful examples. I don't want to remove them. Anyway, what questions, if any?
I got one.
Good.
I got a question. Yeah.
Great.
So I'm wondering about your comparison of the spectrum of Vega with 3C273.
Yes.
And you had arrows connecting up the hydrogen Balmer lines.
Yes.
In Vega, they were absorption lines, and in 3C273, they were emission lines.
Good, really good.
How do you know that they're both hydrogen?
Good question.
Why are they different in the two objects? I mean, they're both hot objects that are, emitting light.
That's a really good question. First of all, if I wasn't stumbling all over myself here, there's the slide you're talking about where
that's the slide. Yep.
These are emission lines here, but that's an absorption feature down there, and so forth. And that comes down to something that I did remove from my presentation because it was just taking too much time, and this is a ding moment. I really didn't want people to think that they had to do a lot of astrophysics in order to excuse me, again, I'm tough. It's difficult for me to multitask when it comes to Photoshop. I didn't want people to think that they had to do a lot of astrophysics in order to understand this. So let's look at this slide again when I was talking about these absorption lines occur when an electron moves up. And the way I like to think about it, it's sort of like if you grab a ball and try and pull it away from a magnet, it takes energy. And so that's absorption, meaning that there's a dip. But later on, if something if an electron drops from here down to there, it releases energy. Like when you drop a tennis ball, it's at a lower energy potential when it's down low. So whether you get emission lines or absorption lines depends on some of those things that I also glossed over with reference to Kirchhoff, and that is how the electrons are jumping and what gases they're moving through. That was this slide. So sometimes we get absorption lines and sometimes we get emission lines, and which you get depends on the temperature of the gas. If the gas is being excited by an outside source, you get emission lines like a neon gas tube or a neon sign in a pizza joint, although they're all LEDs today. Or if the gas is cooler, like on Vega, then it absorbs and you get an absorption line. But that's a great question. I raced through the answer now. I hope that was helpful and not too much. And actually, you don't need to understand in order to do what we're talking about. That's the kind of knobs that you might read as I have. And actually, there was a professional who gave a lecture at the AVSO meeting this weekend, and he was talking about this too. And I went, do I really understand this? And I had to sort of think it through again. So, but you're looking for features. Whether they're absorption or emission lines is a second level of understanding. Good question, though. I appreciate your spotting that and asking about it. Other questions anybody might have? That's it.
I have a question. I have a question. Is this something that it seems like you're encouraging amateur astronomers to get into this because it will help the greater good of astronomy. Is that right?
I think that's true. I mean, I'm a businessman. So unfortunately, everything I say is going to be considered with the taint of, is he just trying to sell us stuff? Someday.
No, I understand. Yeah.
No, yeah. But I mean, the reason I like it is because I sometimes feel like Santa Claus with new users, because they get so excited when they capture this stuff. It is like that first image that sometimes people have captured in the moon. And so it's not only for the individual, but also in terms, it is a greater good. The more people that understand, the better. And it's a great outreach tool. The story about Neil deGrasse Tyson, I wish my meetings with him were sort of like, yeah, we sat and had coffee in the lobby of his hotel or something, but it really wasn't that at all. I stood outside the theater where he was talking here in Seattle in the pouring rain. And, you know, I've done that 3 times, and I don't think I'll do it again, because it sort of feels like a pauper waiting for the king to come along, like celebrity worship. But he's got 13 million Twitter followers. All I want is one shout out, Neil. Just one shout out about my poster. And then instead of my wife sitting in front of the TV stuffing posters into a tube, we'll have some high school kid in a garage stuffing posters. So, but it was the 3rd episode of Cosmos where he talked about spectroscopy. And a fair number of people, when I'm doing outreach with the public, actually remember that. So
I saw that episode. Yeah,
that's cool.
It creates some interest that people may have. And actually, I've got one other thing to show you, speaking of outreach, and that is, I like my sleep. I like sleep hygiene. I like doing stuff during the day. I like seeing the people that I'm showing the sky to. So I like doing solar astronomy. I've got a Lunt 100. I go out here, and it's wonderful. Adding spectra to that experience is just another tool in your bag of tricks. And I want to show you a video here. It's really short, and you're going to hear the audio in the background. So this is me in my front yard showing, this is a high-end solar spectrometer. It's got this gnomon here. You don't even need tracking. You just point it approximately at the sun. But because it has a slit, you're only looking at a little window. So you have this little tuner here that lets you tune to what part of the rainbow you want to be looking at. Right now, I've tuned it by just moving that lever to what's called the magnesium triplet. Magnesium has 3 lines right next to each other for reasons that are way over my pay grade. They're quantum mechanics, apparently. But let's look at this. It's like the most awful video you can imagine. It's my iPhone at the eyepiece. So I was making this to show a friend what he could expect. And it'll get a little better than that. There is the magnesium triplet. Now, while we're focused on that, you'll see the colors change as I move that lever.
I can't see it. I don't see it.
I forgot to share my screen. Hold on. I can't believe it. Thank you. I thought I heard you interrupt me a moment ago, and I just talked right over you.
We only see the enjoyment on your face, but not the video.
You can see that now, right?
Yes.
Okay, my apologies. So there's the device with a gnomon at the top, no tracking on the bottom. There's that lever that's pointed right at magnesium. And now I'll just drag through here. There's the view of the magnesium triplet right there. And now you'll see the colors change as I move that lever. Give it a second. There, now it's into the blue. That's a hydrogen. This prominent line there is hydrogen alpha. So this is the kind of thing, and I'll just show you a couple more things. There's what's called the sodium doublet. So this is the kind of thing that you could augment solar outreach with, where you could have somebody just stationed at that and get into a little discussion about what spectra is or are. Now, the only problem is this is a higher end device. It's like $1,200 bucks. So that's the kind of thing you want your club to buy after you've sold a few more binoculars. But yeah, so I think there are lots of advantages to clubs doing this kind of outreach. Other questions? Well, I'll show you one last thing, and I'll leave you with this, and that is.
I got a question, Tom.
Oh, great, Dennis. Go ahead.
One last thing. Was there some aha moment in your career that, as an astronomer, that got you excited about doing spectroscopy?
If I knew that moment, I'd recreate it tonight for all of you. I don't, actually, Dennis. I just think I realized I wasn't going to be an imager, and I wanted to do some science. I mean, I was, like most of us here, we've always had an interest in science, and I wanted to understand a little bit more. I just wanted to do some instead of just read about it. So there was no...
Well, okay, then what was the coolest thing you ever made a spectrum of?
That's a really good question. And in terms of thrill, it was my first spectrum of Vega that I started with tonight. the only thing I can liken it to, it's a equally esoteric example. In the 70s, a friend of mine built a dish to capture satellite TV. He was, living up in Richardson Grove in Northern California. There was no cable. And I can remember setting that thing up, and and you have to point it at a satellite that's nowhere to be seen. It is,
Right.
It's a dot in the sky. You can't even see it. And we had a little winch, a little hand winch, and we sort of figured out where it should be. We had a TV hooked up to it. We went crank, crank, crank. And with one pull of that, at one point of that winch, it was pointing right at the satellite, and the TV popped on with crystal clear color. It was like, wow. Well, it was the same thing, I think, when I saw those first dips of Vega. It's like, wow, I can do that. It's amazing.
That's cool.
The examples I showed you tonight, I think really the accelerating shell of a supernova, to be able to measure that kind of thing. I honestly can't remember whether I shared it with you tonight. The idea of going into schools and doing mentoring. Did I mention that tonight? Yes or no?
I think you did, yeah.
Yeah, because thank you. You can take this, and there's no reason every one of you can't mentor some student, or at least go in as a club maybe to the school, to an astronomy teacher or a physics teacher. Physics teachers like to teach spectra. Chemistry teachers have to, because it's so intrinsic to the whole idea of chemistry and chemical bonds. You could go to them and say, hey, why don't I come in one evening? That's the problem. I mean, after COVID, which is an easier expression to say now than it was a week ago, given what we're hearing about potential vaccines. But it's the kind of thing that again, could augment your relationship with the community. And it's just so nourishing. It's a great question. Dennis, you all asked good questions. I appreciate it. Robin, your question was the first time I've heard that question in the way you asked it. I appreciate it. Any other questions? I know I've gone far longer than what I promised.
No, I love your passion. I have learned so much. I have learned so much science tonight from your discussion. Kind of things that were kind of filtering in the back, but I didn't understand them. But you brought clarity. So thank you so much for that.
Thank you.
Yeah, my pleasure. I wish you all well. Don't forget to do that outreach. It's the way we give back. Pay it forward and pay it backward for the opportunities we had and were able to take advantage of.
Yeah.
Thank you all. Good night and enjoy yourselves. I'll leave, and now you can talk about me behind my back.
All right, thanks, Tom. Thanks for coming.
Thank you, Tom.
See you all. Good night.
Thank you.
Bye.